Hello and welcome to Linear Regression Module 2, Leaves and Trees, where we'll take a more in-depth view of linear regression and look at specific examples. I'm Dr. Mark Williamson at the BERD Core for DaCCoTA at the University of North Dakota. So linear regression is a foundational statistical technique to the simplest linear regression to the most complicated multi-level model. And it takes on many forms. I outlined in our first module a bird's eye view, 4 kind of ways to look at it, a broad outline from single, multiple, multivariate regression to the characteristics between the predictor and the response variables that result in different types of regressions, as well as other considerations like truncation, time series, etc. So today we'll look at more details at the mathematical, statistical underpinnings, as well as going through several concrete examples. Because at the end of the day, regression, you want to understand what you did and be able to defend your results and not have your results be ridiculed because you didn't understand them yourself. Let's start by asking some rationales. So when should you use linear regression? In layman's terms, you would use it if you wanted to predict a variable's value, say a y variable. Or another way of putting it, you want to model the relationship between a y variable and an x variable. Because this y variable is usually something you care about, like disease incidence, some sort of characteristic of personality, etc. So that's kind of like the big picture questioning. So more practically with your data, you'd use linear regression typically when both y and x are numerical. Now it's not always the case. You can, that's the most normal case when y and x are numerical, but if it's categorical, you can still use regression that's logistic. If there's a combination of your x variables of categorical numerical, regression works fine. If your y is numerical, your x is categorical, that's typically what we would call ANOVA, though statistically underlined, they're really kind of doing the same thing. It's just more convention to call it ANOVA as opposed to regression, but really you can think of ANOVA as a specific type of regression. The only time you really can't use regression in this sort of schema is when they're both categorical. And then finally, when you should use it, the linear part is if you expect there to be a linear relationship. In a very simple example, it'd be a linear line between the x and the y. Obviously, if there's no expectation of linear regression, you shouldn't use that. You should try a nonlinear approach. Next, let's ask what assumptions are there for basic linear regression. I use the word basic to say that the data is relatively uncomplex and that the y variable is normally distributed. So the 4 typical assumptions are linearity. Once again, you expect a linear relation between the y and the x. Next one is homoscedasticity, which this is the variance of the residuals is the same for any value as the x. So essentially, the variability is the same across x. So if you look at the residuals, you expect to see the pattern of it to be pretty straight. You don't want a shotgun or like an arrowhead blast. You typically look at this after you run the model through looking at your residuals versus fitted, and we'll go more into detail what we mean by residuals and fitted, but it should kind of have this more even pattern. Another assumption is independence, that observations do not depend on one another, and this really depends on your experimental design. If you had a study where all your observations came from one person telling another person to come do your study, that might not be independent. You really have to set this up instead of necessarily testing for it after the fact. And finally, normality for basic regression. That means that your y variable follows a Gaussian or normal distribution. You can check that typically by histograms or QQ plots. The histograms, if the normal distribution is for that kind of bell-shaped curve, symmetrical. And a QQ plot also is a way to look for normality where these dots should kind of fit this line as best as possible. There are other sorts of regression which don't have this assumption, but it's useful to start with kind of this basic idea. So let's get into some descriptions now. So when I talk about variables, I'll a lot of times use y and x because that's just conceptually you can think of a scatter plot. It's easier to remember which one's which, but y variable is the one we usually care about. It's also known as a response, measured, or dependent, where the x variable is usually used to predict y. And they're also known as predictor, controller, independent variables. And now let's get into fitted or predicted values. This is when we're actually running our regression model. We get this equation, and so our predicted variables are the values of y we generate by plugging x into our completed model. So we have our x variables, we have the different coefficients, and then some sort of error term. So we're trying to predict y. And so it's also essentially the line of best fit if you have a visual plot. So the fitted variables are essentially this line, where the residuals is the fitted values minus the actual observed values of y. It's sort of this error prediction line here. The green are the observations, the line is the fitted line, and then error prediction residuals. So what this is all leading to is what regression is essentially doing is this procedure of ordering least squares, where you're using mathematics to what's going on under the hood when you're running this on the computer is that you're trying to minimize the square distance between each y value and the line. So you want this line that reduces the error prediction, reduces the residuals to the smallest amount. And we use the square distance for mathematical purposes to create this line of best fit. So then this line best lines up and is closest to all these observations. So then when we actually use our equation to say predict y, it'll hopefully get us that best fit. But of course it's not perfect. That's why there's always sort of error. Some other descriptions to keep in mind as we go forward. Obviously there's different variable types. There's numerical, discrete, and continuous. There's ordinal and nominal categorical variables, and then of the categorical there can be fixed or random. We'll go more into that in our third module, but just for quick and dirty term, fixed are typically categories that we set ourselves, like say treatment groups, and they include everything we care about. Whereas random is more like say hospitals, they're a subset of all possible groups, and they have much more variability. And then finally, just keep in mind that this idea of distributions. So basic regression, like I talked about, assumes a normal distribution, but that's not necessarily need to keep regression to just that. There are a lot of other distributions that data might fit that we can actually run different types of regression with those distributions. Like a Poisson regression uses Poisson distribution. Binomial is often used in conjunction with logistic regression, etc. So there's a whole range of techniques to use beyond basic linear regression that really helps fit a wide variety of data. So now let's walk into some step-by-step examples. We'll start with more the basic linear regression understanding, and we'll use this youth risk behavior survey. This was data collected for high school students on various risk factors, and for our purposes we want to ask 3 increasingly sophisticated questions. First, the simplest, can we predict weight from height? So we have weight of these different students and their heights. We want to try to predict weight. Then we can add in age as well, and then finally add in 2 more actually categories, gender and race and ethnicity. So how we'll work through this is kind of a general process where we'll want to kind of summarize data. This is kind of for any really statistical analysis. Summarize data, check assumptions, run our model, see how well that model fit, and we might have to iterate a few times through this process before getting our results in some sort of presentable form. So with that, let's get started. So I'm going to start out here with our code. So we're going to get our data set in here, take a look at it with head. You can see here we have height in meters, weight in kilograms, race, sex, age. We also have this other category that we're not going to use right now, so it's important to understand what your data is and what you are and aren't going to use. So for a simple example, we'll just use height and weight. So let's summarize them. So looks like mean, minimum, look at mean, height, and weight. There we go. Let's take a look at histogram to see if they fit our assumptions of normality. And we really only need to worry about weight, but often if we just have a single x, single y, if you transform y, you also want to transform x. It makes it easier to visualize. So I think let's transform. So this doesn't quite have a normal distribution. So all that happens is we can transform it. We'll transform it with log, and that approximates better. And I'd say, yeah, that's close enough. I think we can keep moving forward. So with that, let's do our linear model. So we're going to use LM and R. So we're going to have weight, the natural log of weight, as a function of height. We're going to summarize that. It was our model formula, residuals, but then two important parts here, the overall model. If it was significant, we have a statistic. So any sort of model result, we have a test statistic and a p-value associated. So the test statistic is this f value here, and the p-value is significant, so the overall model is significant. We look at our specific variable height, that is, we have a t-value that is also significant. So another important part here, we can see kind of how much height helps predict weight by this r squared. Let's just take a look at adjusted r squared. There's kind of a bit of differences between the two, but adjusted r squared is probably better. And we see that it accounts for 0.24, so about 24% of variability. So finally, we're going to plot our residuals with this here, and this code just makes it so we can plot all four at once. The residuals look pretty decent, so we can kind of see. Not too bad. I think that's good enough. And we'll do our scatter plot of weight and height. And then we added a line of best fit by getting our slope and our intercept and slope out. And we can see here that as weight goes up, so does, or sorry, as height goes up, so does weight. So, okay, looks all right. So now let's look at the more complicated by adding an age. Now let's plot and take a look at just kind of age by weight and height. And so far here we see the age is integer, and so far it doesn't look like age and weight have much to do with each other, so we're not sure how much age is going to affect it. And then we're also looking at age and height because they're in the model together, and if they're too correlated, that's can lead to issues with multicollinearity, which can mess up your model. It doesn't seem like there's too much going on, but good to check. So now we'll do our linear model again, and now we're going to use this formulation, which is height apostrophe age, which is going to mean height, age, and then the interaction term between the two. And when we do the summary, we can take a look here. The overall model is significant, but then when we look at the individual coefficients, height, age, and then the interaction shown by the colon here, none of those is significant, which leads me to think that there's actually probably a collinearity problem with age and height. So looks like adding age did not improve the model. And then the residuals, they look okay, but we have other reasons to believe this model isn't that great. So now we'll wrap up these set of examples with the most complicated model, height, age, gender, and race, trying to predict weight. And we're actually going to cut out age because we saw in that simpler model that it was problematic. So since these are categories, let's do box plots to see how they relate to weight. And we can see here gender seems to be pretty well balanced, but race seems to be pretty imbalanced. So I'm going to take a look at a table of observations by race. You can see here that there's missing values. Some races only have a few observations, like American Indians, Alaska Natives. So we're actually going to subset our data and just look at 3 race/ethnicities. We look at, just include blacks, Hispanics, and whites. And when we do that again, this is the table below, we see what we only have those three there. And they're pretty clearly represented. And if we do, we'll get our new natural logs of weight and heights. We're going to factor race and do a box plot of just those three, and that looks pretty good. So now we'll do a third linear model, so weight as a function of height, sex, and race. With the summary here, we see that the model is significant, and now there's a little different interpretation with categorical, but we'll start with height. That's again significant. And now here, since they're categorical, you kind of have to dummy variable it. So there's sex male, and that's compared to the sort of default, which just says female. Looks like there's no significant difference. And then since there was three variables for race, you compare the one Hispanic against, looks like the default's black here, no difference. But then whites compared to the default blacks, there's a significant difference. And the coefficient estimate is negative. So what that is saying here is whites have significantly lower weight than blacks. And you can kind of see that a little bit in this box plot. So then the thing we see here is the adjusted R squared is 0.23. So not a lot, but keep that number in mind as we keep going here. And then residuals, they look okay. All right, so let's compare some models. So there's more sophisticated ways to do things. We're just going to do something quick and dirty. We can use ANOVA to look at different models. Since we save our linear models as variables, we can just do ANOVA for 1 and 2. So that's looking at height and then height and the interaction of age, height, and then those individually. You can see here that what we find here is it looks at like the residual sum of squares, and it's actually lower, so lower is better for number 2, and that's significant. So what this is saying is actually this model explains more of the variation. But since we saw that there's issue at age, we wouldn't just trust this by itself. I would say it'd still be better to just look at this alone compared to the other two. All right, well, let's look at the more complex model. So since we subset that model, with the sex and race, we'll need to subset our simplest model. So we'll do that here, create a linear model 4, which is just that basic. We can summarize it here. Again, we see that height is significant. Now we have an adjusted R squared of 0.21. That was compared to that R squared of 0.23 for the more complex model. If we do a comparison between them, between the simplest one, the more complex, again, the residual sum of squares is lower. It's more complex model, and that's significant. So we'd say that, yeah, it looks like, it's not a lot, but it looks like this more complex model explains more of weight than that simplest weight and height. So obviously, when comparing models, this is kind of a pretty basic way. I would use something more sophisticated like AIC, like ACCI information criteria, which we'll go into more depth later on. But this is just an important step in your model building. You might want to compare different models to see which one works the best. All right, so now we'll kind of pivot here to do a quick assessment. What I suggest is for you to pause this video and work these out yourself before joining back with me for the answers. Welcome back. Let's take a look at these answers. For number 1, the 4 assumptions, well, that was linearity, homoscedasticity, independence, and normality. Again, this is for basic linear regression, which assumes normality. That leads into number 2. Well, can you still run regression if there's not normally distributed? Sure. You can use things like logistic, Poisson regression. We'll see in our next example. These are all examples of a generalized linear model, which doesn't assume normality. It uses different distributions. For number 3, to fill in the blanks here, the red line, that's your fitted or predicted values, where the blue dots, there's your actual observed values, and then the black line are the residuals. We're running ordinary least squares means to find this line, this predicted value of best fit, to minimize the residuals. For number 4, we have output from a basic regression where distance is a function of speed, and speed is indeed significant. The p-value is kind of odd here, but it's much less than 0.05, so it's significant. And looking at the adjusted R-squared, we would say it's almost like 2/3 of the variation is explained by speed alone, so that's a pretty strong association. And 5, if you want to have this more complex model, you're going to want to use part F, which is income as a function of IQ, and then age, gender, and the interaction. That's what this tells us. And then region itself. For example, you wanted just the interaction of age and gender, and not age and gender specifically as well. You'd use this sort of scenario, though it's typically the best practice is to include, if you're going to have an interaction term, you include the individual terms as well. Okay, let's pivot here out of basic linear regression that assumes normality to more generalized linear models. So we'll look at a logistic regression using the Youth Risk Behavior Survey, a second data set. It's a little modified to try to predict whether students got into a fight or not by weight. And then we'll ask a more complex question, including more variables. We'll also take a look at this warp breaks data set. It's the number of breaks in a loom, like a weave. And we're asking the question, is the number of breaks different across these two categories, wool type and tension? So taking a look at our simplest logistic, trying to predict whether a student got into a fight by weight. So student got into a fight, that's going to be a binary, like a 1-0 or yes, no. So it's prime fodder for logistic. So I'm going to switch to SAS for the coding. I'm going to import my data. I've abbreviated my data file here, print it out, and see here that's similar to the youth example we used earlier with age, sex, height, weight. Race here is different because we just resigned ourselves to looking at one race, whites. And then we have our fighting variable, which is the raw data here, but then I codified it to no and yes because we didn't really care about how many fights, just whether they did or not. So that's our binary Y variable. So let's take a look at frequency. Turns out that most students did not get into a fight, but about 1/5 did. So to run our logistic regression, we're going to use proc logistic, and we're going to restrict our ages to 3 to 7. That's not 3 years old, but categories. This is like, I think 13 or 14. This is like 17 or 18, because it turns out the lowest ages only had a few entries. We're going to model fighting. It's a function of weight. And I specifically want to model whether or not the probability of them answering yes or getting into a fight as opposed to not. So then there's going to be a lot of SAS code that comes out. I'm only going to show you the really important bits. So first of all, there's a probability of modeling fighting as yes, just to confirm that we set it up the way we wanted to. And here's our maximum likelihood estimates and statistics. You see that weight has a high test statistic, so it's statistically significant, so it helps predict whether they got into a fight or not. And then within proc logistic, its fit statistics compares an intercept only model, so just having the intercept, and then adding covariates, so in our case, just weight. So here's that AIC, and the lower the better. So it turns out if you add covariates, the AIC gets lower, which is a good sign that seems this worked pretty well. And then since I plotted it, I will get this result up here, and we can see that since the Y variable was binary, we get either 1 values or 0 values. So really what we're playing is the probability of 0 or 1, so yes or no. And what we see as weight goes up, the probability of getting into a fight goes up. That's not particularly strong. Even the heaviest students, probability is around only 50%. The more classic shape we see in logistic regression typically is an S-shaped curve, which has asymptotic behavior at the ends. But it just looks like with our data here, there's not a particularly strong relationship, even though it's significant. Righto, let's upgrade our question by seeing if we can predict fighting by sex, age, height, and weight. So we're going to do some more frequency tables to look at fighting by sex and age, since those are categorical variables. These tables have a lot going on here, but let's look at the bottom, which shows the percentages. And we see for ages, for the youngest age to the oldest, the ones that are fighting, 21% shoots up to 24, back down to 21, and goes down from there. So it looks like the students who get in the fights the most are in age group 4. Looking at sex, between females and males, females get into fights about 13% of the time, while males, that's over double. So these tables are really helpful to see kind of what we expect out of our data. So now we're going to run our logistic model, but instead of using proc logistic, I'm going to use proc Glimmix, which uses generalized linear mixed models, so it can use a more broad category that includes logistic. So we're going to again restrict our ages and then include this line here for sex and age to tell our model that these are categorical variables with this class statement. And we're going to model fighting with the event of yes as a function of sex, age, height, and weight. And now Glimmix, unlike proc logistic, you have to tell it what distribution it is. So we need to have this slash distribution, and now we're going to use a binary distribution because we have yes, no, or 1, 0, that kind of thing. And then we're also going to add this statement here, odds ratio, which is going to be the premier way we're going to display our results. So when we run this, again, there's a lot of output. I'll just show you the most important bits. Again, we see that we're modeling the probability of fighting equals yes. Here's our fit statistics. Unlike proc logistic, it's not really looking within the model, but we get this Pearson chi-squared degrees of freedom. This is what I usually look at. It should be around 1 to be a good fit for the distribution. And since we had binary data, it's actually a perfect fit. So that gives us confidence that we've fit our distribution correctly. So here's the test of fixed effects. We see that sex, age, and weight, those are all significant, while height is not. And so rather than plotting these out, we typically would use something called an odds ratio table, and we'll walk through how this looks. So for this first one, we're looking at female versus male, holding everything else constant, and we get what's we have here as the estimate, which is our odds. So what this is saying here is the odds of a female getting into a fight compared to a male is 0.416. So 1 would be they have the same odds. So this is less than half as likely. And we can tell that this is significant by looking at the confidence limits. And since this is below 1, this upper confidence limit should be below 1 as well for it to be confidence. If the confidence limits enclose 1, it's not significant. So let's move on now to age, where now we have more categories. So we're comparing every younger age to the oldest age group. And you can actually set which specific category is your comparison. Here it just worked out pretty well. You can see here for the youngest age, it's actually over. It's almost twice as likely that the youngest age will get into a fight as the oldest age, and that's significant. And it continues to be higher and significant until we get to age 6, which is higher, but we can see now that the confidence limits involve 1. So that means it's, higher, but it's not significantly higher. So there we go. So younger ages tend to get into fight more. Males tend to get into fight more. Now, we can also look at continuous variables, but they're done a little differently. They're assessed as 1 unit offsets from the mean. So what that means here is for height, our control here is the mean, and then we have 1 unit offset, so 2.7 meters. We can see here that the taller people do have slightly higher odds of getting into a fight, but it's in no way significant. But when we look at weight, we see here that weight now, that's the mean, 1 unit increase. There's a very slight increase in odds, but actually that increase is significant, which is kind of what we suspected. We saw from our simple model that it was significant, but it wasn't pretty strong. But what we see here is that the higher the weight increases the odds of getting into a fight, if only slightly. So there we have it. That was our more complex logistic regression. Now let's take a look at Poisson regression by trying to answer our research question: is the number of breaks different across wool type and tension? So these are breaks. These are on like an automated loom. And so we'll take a look at our data here. We see we have breaks, and see these are integer values. You can think of breaks as like 0 breaks, 1, 2, 3. That's the kind of count data we're used to for Poisson. And then now we actually have 2 different categorical variables: wool, which is like A and B, or tension, low, medium, and high. And so we see here that this looks a lot like a two-way ANOVA, and really, many cases really is, though we're using a different distribution. So it's really just kind of semantic whether this is a ANOVA with a specifically Poisson distribution or just a Poisson regression with categorical variables. Because again, ANOVA is really just a kind of regression at the end of the day. So anyways, let's keep going. We'll use proc-limits again, because this is nice and multi-purpose. Where again, make sure wool and tension are class statements to say that they're categorical. We're going to model breaks as a function of wool, tension, and then in SAS, this straight bar means the interaction term. So wool, tension, and the interaction. We're going to make sure we know that it's a Poisson distribution, and we'll go from there. I'll explain these two in a second. So here are fit statistics. We can see the chi-squared degrees of freedom. It's a little high, but since I'm pretty confident that this is Poisson distributed data, and I've seen other examples with this that use that, I'm going to say that it's close enough. So here's our test of fixed effects: wool, tension, and then the interaction term. And we can see here that the interaction term is now an asterisk, so which was a little confusing because in R, the asterisk was one, the other, and both, kind of like this is in SAS. So you just kind of need to keep the intricacies of each language in your head. So looking at significance, all these test statistics are significant. And so because they are, we want to plot them. So that's why I'm going to use this LS mean statement in proc-limits. It's going to take the means out, and we want the interaction term because we're going to plot those both together. Now we also need to add a couple things if we want error bars. These are the confidence limits, and then this I-link. It's a little tricky to explain, but essentially when we're doing a Poisson distribution, we switch the data over to a different scale, and we want to switch it back so our results are interpretable. And then we can output this LS mean data. Using that LS mean data in our proc SG plot, we're going to make a bar plot by wool and tension, and then our responses are going to be our means. And then we're going to have upper and lower limits to get our error bars. So here's just the least squares means. Then when we pull this out here, here is our graph. And what we see from here is that for our type A wool, the tension with the most line breaks, or warp breaks, sorry, is the low tension, while the high and medium tension, they're really not any different. Whereas in type B, both the low and the medium have higher breaks than the high tension. So the big picture I'd take from this is no matter what wool you're using, probably use high tension looms if you can get away with it. Okay, with that, let's turn over to another assessment. Pause here, maybe go get a cup of coffee, work on these your own, and then unpause to get the results. Welcome back. Hope you had coffee. I certainly did. Now for number 1 here, we're asking about types of regression used. Well, for binary response data and count response data, we should use logistic and Poisson like we used for the probability of fighting or the number of warp breaks. So if you want to display the number of observations across groups in SAS, well, that's essentially a frequency table, so we want to use proc_freq. And then generally speaking, on 3 here, what does this following term mean in SAS? Now this is a little tricky because it means something different in R, but in SAS it just means the interaction between variable 1 and 2, whereas in R it means variable 1, variable 2, and the interaction. If you want that same thing for SAS, you need to have a bar to have the variable 1, 2, and the interaction. Tricky, but you'll get it. 4, so there's some output here of odds ratio of logistic regression. So for race, it looks like if we compare 2, 3, and 4 to race 1, the estimates are all below 1, so that'd be lower odds, and all the confidence limits are below 1, so they're significantly lower. Whereas for sex, it looks like comparing 2 to 1, it's higher, and that again is significant. So again, because the lower confidence limit is above 1. And finally, to the right, we got type fixed effects from a Poisson regression. And it looks like year is significant because the p-value is below 0.05, whereas region and that interaction term, they are not because their p-values are not significant. So let's wrap up with some caveats and concerns. The first one I want to bring up is the art of model building. Oh, sorry, not that kind of model. Statistical models. So it really is like an art. There is no infallible set of instructions that will bring you to the end every time. You really kind of need an eye for it. And it takes practice, and it's almost never done. It's never perfect. But you can do your best and be able to defend it. Another caveat here is variable inclusion as you're building your model. Often you can add all sorts of different variables. You want to make sure you're only adding ones that you really think affect your y variable, and you need to make sure that they're not the x variables aren't confounding each other. That multi-collinearity is a real issue, so kind of choose your variables wisely. And then as you build these things, complex models, as they get bigger and more complex, are harder to interpret. So you really want to take your time. You really want to think through each step. And it's often a really good idea to start with a very simple model and build up from there. So you have understanding at each level. So when you get to this complex model, you know what you're seeing. Another caveat, distributions. So we looked at both binary and Poisson distribution. There's obviously many more. And a lot of working with distributions involves trying to understand your data, how it might have been generated, to see what best distribution fits. And there can be multiple possible distributions you might need to try. For example, with Poisson, if it's over dispersed, you might need to include or try a negative binomial distribution instead, or add like a zero inflation consideration for more complex Poisson distributions. So there's just a lot going on there that you need to realize and be aware of. So moving on to model fit, obviously we did some examination of residuals, Pearson chi-squared, even AIC, and so there's a lot to look at, and you want to be looking at these things to make sure your model fits your data well. But it's a delicate balance. Again, it goes back to that art of model building. Two things you want to kind of avoid. You want to find that happy medium between underfitting and overfitting. Underfitting a model is including too few variables that it really doesn't predict very much. Kind of like our weight and height. The height only model didn't really predict too much about weight, so we might want to include more variables. Whereas overfitting is you had a bunch of variables, which helps model your data set very well, but the problem is it's not generalizable because you've fit your specific data so well that it's really not going to fit any other kinds of data very well at all. And so that doesn't really help you answer questions about future data. So you don't want to involve too many variables and get into that problem. Next, let's talk about computing considerations. As you kind of saw here, there's a lot of ways to skin the statistical cat, as it were. You can do the same procedures across different softwares, like I used SAS and R. You can use SPSS, Stata, whatever. And even within programs, there's different functions that do the same thing. Like I use proclogistic and proclimix to do logistic regression in SAS. So you can use what works best for you. And finally, with computers, the big mantra with computers and statistics is computers are fast but dumb. You're going to need to be the one who understands what you're doing. You can put a bunch of random stuff into a statistical model and run it, and it'll output stuff. But that output might be junk if you did it incorrectly. The computer is fast, it just does it, but it's dumb. So you need to be the one who has the understanding, that has the brains, that knows what's going in, so you can interpret what's going out. And then finally here, this would not be a regression talk if we did not have something about correlation and causation. That's like having a big explosion and having nobody walk away from it without looking back. So, correlation, of course, does not imply causation. For example, here, there's a lot of these funny graphs where they correlate random, really related events, like number of people drowned and Nicolas Cage. There's a correlation, but we're in no way saying that Nicolas Cage's films caused people to drown. You have to do more work to get the underlying causation if there really is something there. Correlation by itself does not imply that. So there's my little obligatory comment upon that. I want to leave you here with some real-world examples. This first by Zero et al. Is just a really great protocol for conducting and presenting regression type analyses. I mean, it's really, really well done. He has actually 10 steps. So I would defer to Zur when it comes to any of these things. I'd take his word, not mine for it. And he does a great job of presenting. For example, these are some great ways to present results. This is a Poisson model. You can see here the different variables, the estimates, z-value, p-value, pretty slick here. And he even shows ways of presenting results in graphical format of rather complicated interactions. So great things there. Turning to another paper on physical activity, sports participation, and suicidal behavior. This is a great example of what a typical logistic regression will look like. He's looking at the probability of suicide behavior. And what you often do in these types of studies is you have things that you're interested in, like physical activity and sports participation, but then there's all sorts of other variables that might contribute that you need to add to your model to control for them. They're often called confounding factors. Typically, you start having a table of all sorts such factors like gender, age, race, certain behaviors, and having general summary statistics about them. For example, we see here that women tend to have a little bit higher suicidal behavior than men, which is going to be important to control for. And then this is the type of results that you would have. They did men and women. I'm just showing men. You can see here, these are different categories of physical activity, sample size, but here's that odds ratio we saw again. You can see here that no physical activity is a reference. You see that low active physical activity is actually significantly lower, because we can see it's lower, and then the confidence intervals are below 1. But then these ones are all insignificant because they include 1. So that's interesting. Even more interesting, if you look at sports participation, those without sports participation had over twice the odds of having suicidal behavior compared to ones who did participate in sports, and that was significant. So that's really interesting stuff, and it's pretty well set up. Final example here. This is from Journal of Ecology using a beta distribution to look at plant cover data. So this is a great example of using a distribution to fit your data well. So the problem with a lot of plant cover, so the idea is you look down like from like a satellite, look at percent of plant cover in a spot. Problem is a lot of times plant cover has a weird distribution. It's either kind of like U-shaped, where a lot of plots have no plants, and a lot of plots have a lot of plants, but not a lot have kind of intermediate. So this U-shaped. It can be L-shaped, where a lot don't, and they kind of wane off, and only a few have a lot. They can even be J-shaped, where you have a lot of plots with a lot, and then very few that have little. And it turns out these are different beta distributions. They actually can fit that kind of data quite well. So they actually did that. Here's some of those kind of QQ plots. These two are beta distributions. You can see that they tend to fit quite a bit more than this just normal distribution along this line. There's a lot of irregularities to that line. So it's a great example of using a distribution to fit your data. So to conclude here, linear regression, it's really just a vast swath of statistical models, and the type of regression really depends on a lot of things, including what your response, what your predictor variables are. You might use different distributions, different considerations. You need to consider assumptions and model fit, and remember that this is an iterative process. You might have to go through several models, several steps. So I would ask you to really take your time on this stuff. It can take a long time to get it right. So thank you for joining us for this Leaves and Trees. Tune in next time for a plunge into advanced topics of linear regression, Module 3 deep dive, in case you haven't had enough and you're thirsty for more. So I'd like to acknowledge DaCCoTA, as I am part of the DaCCoTA project, Cancer Collaborative on Translation Activity. We're supported through NIH under this award number. So if you found this supremely helpful for you and your research, please acknowledge us in this sort of manner in any publications or presentations. Thank you and have a great day.